Imagine, just for a moment, that you are tasked with rewriting the underlying code for the physical
Oh
universe.
boy, no pressure.
Right. None at all. You need to model the precise movements of celestial bodies, predict eclipses down to the second, and calculate infinite geometric curves.
Okay, so a massive computational workload.
Massive. But here's the catch. You do not have a supercomputer. You don't have a CPU. You don't have a calculator. You don't even have, like, paper.
Wow.
Yeah. You are sitting in a lush tropical river valley in the 14th century, and you are scratching complex, universe-altering mathematical algorithms onto dried palm leaves using a metal stylus.
That is just, it's a crazy visual.
It gets better. You're doing it in the form of Sanskrit poetry.
See, that sounds like a premise for a science fiction novel, right?
Right.
Like a highly advanced civilization using what seems to us like primitive technology
Yeah.
to achieve absolute computational mastery.
Right. But this isn't fiction. This is the actual verifiable history of mathematics. And it completely, it shatters the timeline most of us were taught in school
Yeah, it really does.
because you know the standard timeline, the one that feels like a clean software version history. We're taught that version 1.0 was ancient Greece, where they figured out geometry.
Right, the Greeks get geometry.
And then version 2.0 was the Islamic Golden Age, bringing us algebra.
Yep.
And then there's this massive gap, like a dark age, until version 3.0 just magically drops in 17th century Europe when Isaac Newton and Gottfried Wilhelm Leibniz simultaneously invent calculus.
Which is a very comforting narrative.
Yeah.
We inherently like our history to be visible, linear, and neatly categorized into specific eras led by undisputed, isolated geniuses.
Totally.
But history, much like the physical universe itself, is rarely that neat.
It's completely broken. When you actually step into the world of medieval Indian astronomy, that straight line just snaps. The historical landscape is completely inverted.
It really is.
And that is exactly why we are so thrilled to welcome our specific audience tuning in for this deep dive today, you, the Sigma Scholars of Edward Little High.
Welcome, everyone.
Because we know you guys aren't just here to listen to a history lecture. You are here to build things.
Exactly. We are about to completely reformat your understanding of where advanced mathematics comes from, because the foundational concepts of calculus, infinite series, and algorithmic optimization, the very math that powers modern computer science and physics, they were actually discovered and utilized in medieval India almost 300 years before Newton or Leibniz ever picked up a quill.
300 years. I mean, it's wild. So our mission for this deep dive is twofold. First, we are going to completely immerse ourselves in the rich humanitarian, cultural, and social context, what is known as the Madhava School and the Kerala genesis of calculus.
Right, because we really need to understand the society that breathed life into these equations.
Exactly. And second, and this is specifically for you, the Sigma Scholars, we are going to translate this ancient mathematical genius into 5 distinct Python programming projects.
Oh, this is the best part.
Yeah, you are going to explore, code, test, and mathematically prove the genius of the 14th century using the tools of the 21st.
Which is really the only way to truly understand it,
Yeah.
honestly. To comprehend the logic of the past, you have to run it in the present.
Yeah.
It's one thing to hear about a formula, but it's an entirely different level of understanding to watch that formula compile and output the exact same planetary coordinates that an ancient astronomer calculated by hand.
Totally. And we have a phenomenal stack of sources guiding us today. We are pulling heavily from excerpts of the book A Passage to Infinity, alongside this deep well of historical mathematics papers, newly translated palm leaf manuscripts, and detailed encyclopedic entries that outline the staggering achievements of the Kerala School of Astronomy and Mathematics.
Yeah, and to really ground ourselves, we have to start by zooming in on the map. We're traveling to the Nila River Valley, which is also known as the Haratappuja River, down in central Kerala in the southern tip of India.
Okay, so southern India, and what's the timeline here?
Our timeline begins roughly around 1340 and stretches all the way into the 1800s. And the spark that ignites this entire multi-generational intellectual revolution is a visionary mathematician named Madhava of Sangamagrama.
Madhava, the man who essentially looked at the strict, finite rules of ancient algebra, found them utterly insufficient for what he wanted to do, and decided to just take a running leap into the infinite.
That's a great way to put it.
But before we even touch the math, before we get into limits and loops and arrays, we have to talk about where he lived, because math doesn't happen in a vacuum, right? It is a product of its environment.
It is, and the environment of the Nile Valley was exceptionally fertile for this kind of intellectual explosion. This wasn't a place where isolated scholars locked themselves in ivory towers to stare at the stars in secret.
Right.
The Nile Valley was the cultural cradle of Kerala. During this exact period, we see the modern Malayalam language finding its final form and structure. But more importantly, the society itself was incredibly holistic in its approach to knowledge.
I found this part of the sources fascinating, actually, because today we compartmentalize everything. Like if you study computer science, you're in the engineering building. If you study poetry, you're in the humanities building.
Yeah, never the twain shall meet.
Exactly. But in medieval Kerala, literature, the arts, Ayurvedic medicine, astronomy, and mathematics, they were all deeply interconnected threads of the exact same cultural fabric.
Yeah, a mathematician was likely also a poet. An astronomer was likely versed in Ayurvedic medicine. They didn't see the boundaries between disciplines that we enforce today.
And what really struck me in the texts was the egalitarian nature of how this knowledge was pursued. We often have this massive misconception of the ancient world as being strictly, rigidly stratified.
Right, where only the absolute highest elite, like the kings and the highest priests, had any access to complex knowledge or science.
Yeah, but that wasn't the case here.
Not at all. While it's true that the society operated within a caste system, the historical sources explicitly highlight that profound knowledge, particularly medical science and observational astronomy, was practiced among a very wide section of society.
Which is huge.
For example, the texts note that there were eminent, highly respected physicians and scholars who came from the lower caste Vela or Manon communities.
Which totally shifts the paradigm of how we view that era.
It really does. It suggests an environment where practical knowledge, empirical observation, and undeniable skill were highly valued and shared across social boundaries. If someone could accurately heal a disease or accurately predict the monsoon rains based on celestial observation, their knowledge was recognized.
Right. Results mattered.
Exactly. And that kind of cross-pollination of ideas is essential for any thriving scientific community.
And speaking of a thriving scientific community, we have to talk about the Mamanka Mahatsavela.
Right.
When I read about this in our research, my mind was blown. Try to picture this, Sigma scholars. It is a massive, sprawling festival held on the sandy banks of the Nila River at a place called Tirunavaya. It happens every 12 years, and it lasts for 28 uninterrupted days.
Yeah, it was a massive cultural and religious event. But what is crucial for our deep dive is the deeply practical scientific function it served.
Right.
Astronomers and mathematicians from all over the Indian subcontinent would journey to this specific festival for a very explicit reason: to relentlessly debate, test, and reform their mathematical algorithms.
Okay, if I'm translating this for a modern tech audience, this isn't just a festival. This is a medieval, month-long, open-source developer conference.
I love that comparison.
They were throwing a massive hackathon on the riverbank.
I think using the framework of an open-source developer conference is actually a brilliant way to understand the historical reality, provided we look closely at what they were actually, hacking.
Right, because they are all essentially using this core legacy software, the Aryabhatan computational system, which was developed way back in the 5th century.
Yeah, version 1.0.
Exactly. But over time, they realized the software has accumulated bugs. The mathematical predictions of where the planets should be in the sky aren't matching the physical reality of where the planets actually are when they look up at night.
Right, the model was drifting.
So the community gets together every 12 years, they review the celestial data, they argue over the math, they push their commits, and they patch the algorithms so their predictive models match reality.
Precisely. The sources are very clear on this point.
Mm.
These Indian astronomers were profoundly driven by the need to develop the best possible algorithms because they understood a fundamental law of computational modeling.
Which is?
Over long periods of time, discrepancies between theoretical computation and physical celestial observations will naturally compound and increase.
Right, a tiny error just grows and grows.
Exactly. A tiny rounding error in the 5th century becomes a massive miscalculation by the 14th century. The texts contain explicit statements from these astronomers about the absolute necessity of assembling together, comparing notes, and revising the algorithms.
But I keep coming back to the why. Like, why were they so obsessed with the stars? Why dedicate your entire life and generations of your family's life to calculating the exact position of Jupiter?
Because it was an absolute, non-negotiable necessity for their society's survival and structure.
Oh, so not just academic curiosity.
No, not at all. They needed relentlessly accurate predictions of eclipses, lunar phases, and planetary positions for religious scheduling, yes, but also for vital, practical agricultural purposes.
Right, knowing when to plant.
Exactly. They needed to know exactly when the monsoons would arrive, when to plant, when to harvest. This relentless drive for astronomical precision is what created the absolute necessity for better mathematical tools.
Because you can't track a planet accurately with basic finite algebra. You need trigonometry. And to make trigonometry perfectly exact, you eventually need calculus.
Exactly. The existing mathematical tools simply weren't powerful enough to solve the physical problems their society faced, so they had to invent new math.
And that necessity gives birth to Python Project 1 for our Sigma scholars, the sine table data generator.
This is a great project.
Because to predict the stars, you need insanely accurate trigonometry. So let's look at how Madhava solved this and how you, the listeners, are going to code it.
So up until Madhava stepped onto the scene around 1340, mathematics universally relied on finite procedures. You take a shape, you cut it into a finite number of pieces, you measure them.
Very straightforward.
Right. But Madhava made the decisive paradigm-shifting leap. He moved from finite geometry to what the historical sources call the limit passage to infinity.
Limit passage to infinity.
Yeah. He realized that to get perfect curves, you can't stop cutting. He developed the infinite power series expansions for the sine and cosine functions.
So for Project 1, your task as Sigma scholars is to write a Python script that generates what is known as Madhava's sine table. But the parameters are strict. Your script must calculate 24 incredibly precise sine values. And these 24 values correspond to angles in specific increments of 3.75 degrees.
And to give you some geometric context on why 3.75 degrees is the magic number, it is exactly 1/24 of a 90-degree right angle.
Ah, okay, so 90 divided by 24.
Exactly. By calculating the sine of every 3.75-degree slice, Madhava created a comprehensive lookup table for any trigonometric calculation. And the algorithm he designed to generate these numbers, as detailed by the scholars who came after him, is a beautiful cascading sequence of alternating calculations.
How does the text actually describe the math? Because they didn't write out equations with x and y and equal signs, did they?
No, it's descriptive. The texts outline it roughly like this. To find the sine of a given arc, the arc is repeatedly multiplied by the square of itself, and then divided by the square of even numbers and the radius. It generates a series of terms.
Okay, so if I'm mapping this to Python, you're going to be setting up a loop. You'll take your given angle, your arc, square it, and set up a sequence of iterative divisions by 2 squared, 4 squared, 6 squared, 8 squared, and so on, all multiplied by your radius squared.
Right, that builds your terms.
But creating the terms is only half the battle. How do you assemble them to get the final sine value?
The source text gives very specific instructions for the assembly. It says the terms obtained are to be placed one beneath the other in order. Then the very last term in the list is subtracted from the one directly above it.
Okay.
That remainder is then subtracted from the term next above that, and so on, cascading all the way back up to the top.
Wow, it's a nested, alternating, bottom-up subtraction.
Precisely. It converges on the true sine value. So your Python script needs to replicate this exact cascading subtraction logic to output the table of 24 values.
Okay, but here is where the story gets really interesting, where the second half of Project 1 comes in. Once Madhava calculated these hyper-accurate float values, and we're talking about values accurate to the 7th or 8th decimal place, how did he save them?
Yeah, it's the million-dollar question.
Because, as I said earlier, he didn't have a hard drive. He couldn't export this to a CSV file. And writing out massive tables of 8-digit numbers on palm leaves is just asking for a transcription error when someone tries to copy it down the line.
Yeah, it is a massive data storage and transmission problem. But the Kerala mathematicians solved it using a brilliant linguistic framework called the Kata-Payati system.
Yes, I'm completely obsessed with this. Please explain how it works.
So the Kata-Payati system is a phonetic encoding system. It assigns numerical values not to dedicated number symbols, but to the actual consonants of the Sanskrit alphabet.
Like letters equal numbers.
Exactly. For instance, the number 1 is assigned to the consonants ka, ta, pa, enya. The number 2 is ka, tha, fa, ra, and so on, mapping the digits 0 through 9 across all the consonant sounds.
Okay, but if you just have a string of consonants, it's unpronounceable. It's just gibberish.
Exactly. And this is the genius of this system. The vowels in the Sanskrit alphabet were assigned absolutely no numerical value whatsoever. They essentially functioned as blank spaces, or string formatters.
Oh, wow.
So a mathematician could take a deeply complex 8-digit number, map the digits to specific consonants, and then freely insert any vowels they wanted to turn that string of consonants into a pronounceable word, a meaningful sentence, or even a beautiful voice of poetry.
That is incredible.
You are literally memorizing a poem about a blooming lotus flower, but mathematically, you are reciting the exact sign of a 45-degree angle.
It's a lossless compression and encryption algorithm using human linguistics. This is amazing. So Sigma scholars, the second part of Project 1 is to build a translation function into your script.
Good luck with this one.
Your script is going to take your generated mathematical float outputs, and it's going to convert them into string-based mnemonic codes. You're going to build a Python dictionary mapping the integers 0 through 9 to a designated set of English letters acting as your consonants. Then, write a string generation loop that inserts random vowels to make the output pronounceable so your massive data table can be read as a poem.
It is a phenomenal exercise in data type conversion, array management, and string manipulation.
Yeah.
And more importantly, it mirrors exactly how massive, complex astronomical tables were memorized, stored in the human brain, and transmitted across generations without corruption.
Okay, so we've executed Project 1. We have our highly accurate data table. We have our assigned values safely stored as poetry. But what do you actually do with them?
Right, you need to apply them.
You don't just calculate triangles for fun. You use them to look up at the sky. You use them to track things that move. Which brings us seamlessly to Python Project 2, the Bamboo Climbing Moon Tracker. The historical sources refer to this project by its original name, the Venveroja.
The Venveroja is arguably Madhava's most famous and popular astronomical work. It was composed around the year 1403, and the title itself is incredibly evocative. It literally translates to bamboo climbing.
It's such a strange and specific visual. Why bamboo climbing?
It's a beautifully apt metaphor for the specific computational architecture he designed. If you imagine a long bamboo stalk, you know it has those distinct, equally spaced horizontal ridges or nodes running up its length.
Sure.
The computational scheme Madhava designed requires the mathematician to climb the tree, going up step by step, resting at those measured equal heights to calculate the moon's exact position at that specific moment.
So how does this translate to Project 2? Sigma scholars, your task here is to write a Python program that accurately models the moon's true position in the sky throughout a single 24-hour period. But here is the massive catch, and this is where Madhava broke entirely from the astronomical traditions of the past.
Right, you tossed out the old manual.
The older Aryabhata software, the version 1.0 they were using, relied on epicyclic models.
Epicycles, essentially circles rolling along the edges of other circles. It was the standard way ancient astronomers tried to explain the varying speed of planets, but it only ever gave you an average position over a long period.
Exactly. Your program cannot do that. Epicycles are banned from this project. Your script must use the moon's true daily velocity to calculate its longitude at exact, equally spaced intervals of precisely 36 minutes throughout the entire day.
And we really must emphasize what a massive computational leap this was. Before Madhava, using those older epicyclic models, the very best astronomers in the world could only calculate the moon's position accurately to the minute of a degree.
Which seems good, but
Madhava's Venveroja algorithm calculated the moon's position correctly down to the second of a degree, and it did so at these precise 36-minute intervals. To do this in Python, your implementation is going to have to deeply utilize periodic functions and what the texts call anomalistic cycles.
wait, pause. I know what a periodic function is in code, but what on earth is an anomalistic cycle? I think we need to break that down for the listeners.
Oh, it's a crucial term. The moon's orbit around the Earth isn't a perfect circle, it's an ellipse. Because of this, the moon's speed changes depending on how close it is to us.
Okay, that makes sense.
An anomalistic month is the specific amount of time it takes for the moon to move from its perigee, its absolute closest point to Earth, where it's moving fastest, all the way around its orbit and back to perigee again.
Okay, so it's a cycle based on speed and distance, not just visual phases, like full moon to full moon.
Correct. And the sources note that Madhava's genius was in recognizing a very specific harmonious ratio within these anomalistic cycles. He calculated exactly 9 of these anomalistic months equaled precisely 248 days.
9 months equals 248 days exactly.
Yes. By grounding his math in this cyclical ratio, he created a stable baseline. He could then use his hyper-accurate trigonometry to track the minute fluctuations in the moon's velocity and estimate its true longitude at 9 equally distant times in a single day. Those are the nodes on the bamboo stalk.
This is unbelievable. He essentially built a time series forecasting model from scratch.
Yes, he did.
Sigma scholars think of this project as building an early form of a real-time tracking API. But instead of your code pinging a remote server to pull down a JSON file of satellite coordinates, Madhava used what the historical texts call moon sentences, or Chandravakyas, as his local hard-coded database.
Yeah, the Chandravakyas were essentially lists of constants and pre-calculated positional data stored in that Katapayati poetic format we discussed earlier.
So for your script, you will need to define a cycle of 248 days, break it down into 9 anomalistic segments, and then use a time delta of 36 minutes to output an array of the moon's exact coordinates for a given day. You are literally coding a 14th century celestial tracking algorithm. You are modeling moving bodies in real time.
It perfectly illustrates the paradigm shift of the Kerala school. They transitioned mathematics from static, abstract geometry, measuring triangles on a flat plane, into dynamic, time-based kinematics. They were using math to capture motion.
But capturing motion mathematically inevitably leads to a massive roadblock.
It does.
We've got our sine tables, we've got our time series moon tracking.
Mm-hmm.
But all of this, trigonometry, orbits, tracking the sky, it inherently relies on the geometry of the circle. And you cannot truly master the math of the circle without confronting the ultimate mathematical boss level,
Pi.
Which brings us to Python Project 3, the infinite pi estimator.
This is the specific area where Madhava's genius truly shines on a global historical scale. Because prior to his work, mathematicians all over the world across many different cultures use what the texts call proximate, meaning approximate, values for pi.
Right.
They knew it was a ratio, but they couldn't nail down the exact number. For instance, some of the very ancient Jaina texts in India use the square root of 10 as their value for pi.
I read that in the sources and laughed out loud. The square root of 10, that's roughly 3.16. That is creatively generous.
It really is.
If you build a wheel using 3.16, it's going to be a very bumpy ride. Why would they use such an inaccurate number?
Well, it wasn't about building physical wheels for them. It was about conceptual elegance.
Elegance over accuracy.
Sort of, yeah. The sources explain that ancient Jaina cosmography envisioned the universe as a series of concentric cosmographic islands and oceans. And they believed the diameters of these oceans were measured in grand sweeping powers of 10.
Oh, I see.
So using the square root of 10 for pi made their massive abstract cosmological calculations incredibly clean and easy to manage, even if it completely lacked practical physical precision.
Ah, so it was a feature, not a bug for their specific use case.
Exactly. But eventually, people needed real precision.
Right. Later on, the great astronomer Aryabhata used a much better approximate value. He calculated pi as 3.1416.
Which is much closer.
Yes, but even Aryabhata explicitly stated in his writings that this was only an approximation. It wasn't the absolute truth of the circle.
But Madhava didn't want an approximation. He wasn't satisfied with close enough. He wanted the exact, fundamental mathematical definition of the circle. And he found it not in a static fraction, but in the infinite series.
He discovered the exact infinite series formula for pi. And this is a massive point of historical contention, right? Because in standard Western mathematics textbooks, this exact formula is universally named the Gregory-Leibniz series.
Yep.
It is named after James Gregory and Gottfried Leibniz, the brilliant European mathematicians who discovered it, a full 3 centuries after Madhava had already written it down.
It is the exact same formula.
So let's look at it. Python Project 3 for the Sigma scholars. You are going to build a Python while loop based entirely on Madhava's exact infinite formula.
The formula is beautiful in its simplicity.
It really is. It's pi divided by 4 equals 1, minus 13 plus 15 minus 17 plus 19 minus 111, and so on, off into infinity.
Geometrically speaking, your program is going to mathematically map the deep, hidden relationship between the physical circumference of a circle and the reciprocals of all whole odd numbers.
It's such an elegant loop to code. You just take an initial value of 1 and you set up a loop that simply alternates adding and subtracting fractions of sequential odd numbers.
Mm-hmm.
It is clean, it is simple, it is beautiful.
It is incredibly elegant in theory. But if we connect this abstract math to the bigger picture of actual computer science and the physical limits of hardware, there's a massive glaring problem with this specific formula in practice.
I am so glad you brought this up because I am stopping the deep dive right here. Sigma scholars, if you actually write this Python loop exactly as we just described it, just adding and subtracting odd fractions sequentially, your code is technically correct. The series does converge on pi,
What?
but it converges way, way, way too slowly. I'm talking about a computational nightmare. To get pi accurate to just 5 or 6 decimal places, your computer's going to have to run hundreds of thousands, if not millions, of iterations of that loop.
It is notoriously slow to converge.
Right. And you and I have high-speed CPUs that can run millions of loops in a fraction of a second. But let's go back to the Nile Valley. How on earth did a 14th century mathematician, a man who did not have a microchip, who was doing every single one of these fractional additions and subtractions by hand with a metal stylus on a dried palm leaf, how did he deal with a mathematical loop that converges this slowly?
He couldn't.
He would die of old age before he calculated pi to 10 decimal places.
And this brilliant frustration you're experiencing is exactly what led to Madhava's next, and perhaps most astonishing, stroke of genius. He recognized the exact same computational limitation you just did.
He knew it was too slow.
He realized the infinite series, while theoretically perfect, was computationally too slow to be practically useful for generating the hyper-accurate astronomical tables he needed. He couldn't sit there doing fractions forever.
No way.
He needed a way to jump ahead. He needed to systematically accelerate the convergence of the infinite loop.
Which perfectly sets up Python Project 4, accelerating convergence with error corrections. This is where the math goes from brilliant to genuinely clairvoyant.
Madhava didn't just invent the infinite series. He invented a mathematical mechanism to estimate the exact remainder of the infinite series without actually having to calculate the infinite terms.
Wait, how is that possible?
He applied what the Kerala mathematicians called a samskara, which translates to a correction term or an error term. He applied this to the partial sums of the truncated series.
Okay, I am going to need you to unpack the samskara very carefully because it breaks my brain a little bit.
Sure. Let's visualize the code you just wrote. Imagine you run your Python loop for the pi series, but you force it to stop, you truncate it after exactly 10 iterations.
Okay, it stops at 10.
You have a number, an approximation of pi, but because you only ran 10 steps, it's not a very good approximation. There are literally infinitely many terms left in the sequence that you haven't added up yet.
Right, I'm missing an infinite amount of data.
Precisely. But Madhava figured out a discrete algebraic formula that could accurately represent the sum of all those remaining infinite terms. He called it the error term.
So instead of calculating them all,
By calculating this single separate error term and adding it directly to your short 10-step calculation, you instantly get a wildly accurate value of pi. You don't have to run the loop a million times. You run it 10 times, apply the patch, and get the exact same precision.
that is mind-blowing. Think about what that implies, fundamentally. It implies a profound intuitive grasp of the limit nature of infinite series. He is looking at a sequence that goes on forever, and he's essentially predicting the final destination of the loop without having to actually travel the distance. He's calculating the ghost of infinity.
That is a very poetic way to phrase it, but mathematically, it's spot on. And the source material specifically highlights this as a major distinguishing feature of Madhava's work when compared to the European discoveries made centuries later.
Really? How so?
Well, when James Gregory and Gottfried Leibniz discovered the series in the 17th century, they didn't immediately suggest remedial ways to address its terribly slow convergence. They presented the series as it was.
Oh, wow.
Madhava, on the other hand, provided the infinite series and the algorithmic correction strategy as an integrated package deal. He saw the problem and the solution simultaneously.
So let's lay out the parameters for Project 4. Sigma scholars, you are going to take your terribly slow pi estimator from Project 3, and you are going to give it a massive software update. You will modify your code by injecting Madhava's correction terms into your truncated series. The historical sources actually provide the specific algorithms you need to code.
They do.
You will start by adding his simplest correction term, which is 1 divided by 4n, where n represents the exact number of loops you've run before stopping.
And once you have that working, you will upgrade the code to use his more refined, highly accurate correction term, which the texts define as n divided by 4n squared plus 1.
The ultimate goal of this Python project is performance testing. You are going to write a script that runs the raw series and the corrected series side by side. You will compare the execution time and the decimal accuracy of the uncorrected loop versus the corrected loop.
It's going to be a stark difference.
Oh, yeah. You are going to watch firsthand as Madhava's correction term instantly catapults the accuracy of the output, saving your computer from millions of useless calculations.
To give you a historical benchmark of just how powerful this optimization is, the sources mention a later scholar from the Kerala school named Shankara Varman.
Okay, what did he do?
Using these exact Samskar error correction methods, he calculated the value of pi out to 17 correct decimal places.
17 decimal places.
Yes, 3.14159265358979324. He achieved that level of precision entirely by hand on palm leaves using Madhava's accelerated algorithms.
I mean, I can barely remember my own phone number. The analytical insight required to do that is staggering.
The underlying mathematical concept at play here is described in the texts as the invariance of the truncated series, sum after correction. It's this specific property that allowed the Kerala mathematicians to achieve incredible precision, arbitrary precision, really, limited only by their patience, without requiring a physically impossible number of manual calculations.
It is a 14th century masterclass in algorithmic optimization.
Absolutely.
And from the heights of algorithmic optimization, we finally transition into the absolute core of modern higher math, Python Project 5, integration via samkalitam. Because the ability to master infinite loops and to sum up infinitely small bits of a circle's curve leads directly into what we now recognize as integral calculus.
The foundational concept of samkalitam is what we need to focus on here. In traditional Indian mathematics, the term essentially just means a sum or an addition.
Okay.
But in the highly specialized context of the Kerala school, it evolves to mean a very special kind of sum, specifically a sum whose limit is an integral.
But how did Madhava conceptualize integration without the modern mathematical notation we use today? He didn't have the long S symbol for integrals that Leibniz invented.
No, he conceptualized it geometrically and algebraically. His derivation involved taking a curve, specifically the arc of a circle, and breaking it down into infinitely small, perfectly straight segments.
Like little atomic pieces of a curve?
Yes, and the Sanskrit terminology they developed to describe this process is deeply fascinating because they had to invent words to describe the infinitesimally small. The texts use the word shunya prime.
Shunya pram. What does that translate to?
It roughly translates to of the nature of zero, but the context makes it clear that it is crucially not actual zero. Is a quantity so small it approaches zero, but retains a spatial value.
Oh, that is such a subtle but vital distinction. It's not nothing, it's the infinitesimal. It's the dx in modern calculus.
Exactly. They also frequently use the word anuprime, which means atomic or the size of an atom. They were dealing with physical quantities that were infinitesimally small, conceptually slicing macroscopic geometry into atomic widths so they could sum them all back up into a perfect whole.
So for Project 5, Sigma Scholars, you are going to write a Python script that mathematically simulates Madhava's geometric proof for integration. You are going to take an arc and you are going to divide it into a specific number of equal parts, which we will call n. Your script will first calculate the discrete sum of these parts using a standard for loop.
But this is the crucial moment where we have to highlight a massive fundamental difference between how the Kerala school approached calculus and how modern European calculus is taught in high schools today.
Yes. Let's talk about the Kerala calculus twist, because this completely changes how you structure your code.
Right. In the standard European calculus tradition, the Newtonian and Leibnizian tradition, when you want to find an integral, you typically take the limit first to isolate your infinitesimally small differential, your dx, and then you perform the integration, the summing up, across those differentials.
That's how we're all taught to do it.
Madhava's conceptual process was entirely inverted.
He flipped the script.
He did.
Huh.
Madhava performed the summation of the discrete parts first, using incredibly complex algebra to find a formula for the sum of n parts. And only after he had completely resolved that summed algebraic expression did he set n to approach infinity to find the ultimate limit. He summed the finite to derive the infinite.
Which begs a very practical question when you're trying to code this. How big is infinity in a 14th century textbook? What number do they actually use to represent it?
The foundational text of the school, the Yuktapasa, explicitly tells the student to set the value of n to what they call paradam, and paradam is a specific number. It is 10 raised to the 17th power.
Okay, Sigma Scholars, listen to me very carefully. I am putting a massive flashing warning label on Project 5 right here. Please, whatever you do not attempt to actually run a for loop in Python 10 to the 17th times.
Good advice.
Do not type 4i in range 10 to the 17th power. You will completely freeze your IDE, you will likely crash your computer, or at the very least, you will be waiting until your 10-year high school reunion for the script to finish executing.
That is a highly necessary disclaimer. We want to simulate the math, not melt their motherboards.
Exactly. Instead of brute forcing it, your Python script should model the asymptotic limit dynamically. You'll program Madhava's algebraic sum into a function, and then use Python to evaluate the behavior of that function as you manually pass it exponentially larger values for n, like say 10 to the second, then 10 to the fourth, then 10 to the sixth.
Right, you step it up.
You will plot the output, and you will watch the curve flatten out as it reaches the asymptote, yielding exact, clean fractions like 13, 15, and so on, which mathematically proves the integral. It's about using the power of the code to dynamically prove the logic of the mathematical limit.
And by successfully coding that simulation, you are effectively running the algorithms from the very first textbook on calculus ever written in human history.
Which brings us to the final and perhaps most important question of this entire deep dive. We've talked extensively about Madhava and his genius, but Madhava himself didn't leave behind a massive library of step-by-step textbooks, did he?
No, he mostly spoke his teachings and wrote in those dense, poetic verses we talked about.
So how did all of this brilliant, fragile mathematical knowledge actually survive the centuries? Who carried the torch and wrote it down?
The survival and expansion of this knowledge is entirely thanks to an unbroken lineage of brilliant disciples who formed the Kerala school. And the most crucial document they produced is the text I just mentioned, the Yuktapasa. It was written by an extraordinary scholar named Jistadeva, right around the year 1500.
And just to be completely clear, the historical sources we are reviewing state unequivocally that this text, the Yuktapasa, is considered the first comprehensive textbook on calculus in the world.
Without a doubt, it is
Yeah.
historically monumental. But what makes the Yuktapasa such a revolutionary and historically vital document isn't just the advanced math it contains. It's the language Jistadeva chose to write it in.
What language was it?
Crucially, he did not write it in the elite scholarly language of Sanskrit. He wrote it in the everyday vernacular language of Malayalam.
Why is that such a massive deal? I mean, a math textbook is a math textbook, right?
Not in that era. Writing it in Malayalam democratized the knowledge completely. Previous Sanskrit texts were incredibly dense. They were written in cryptic, condensed verses designed specifically for rote memorization by a very select, highly educated few.
Oh, so they were exclusionary.
Yes. They gave you the formula, but they didn't show you the work. Jestadeva changed everything. He wrote in conversational Malayalam specifically to provide non-technical clarity to the reader.
He wanted people to actually understand it, not just memorize it.
Exactly. He included exhaustive, step-by-step proofs, which were called upapati, derived from absolute first principles. He didn't just hand the student a formula and say, trust me, this calculates the moon.
Right.
He took pages to explain the why and the how. He walked the reader through the geometric logic, making the most advanced mathematics on the planet completely accessible to absolutely anyone who could read the local language.
Which perfectly aligns with that egalitarian, holistic, integrated culture of the Naila Valley we talked about at the very beginning of the deep dive. The knowledge wasn't locked away, it was shared.
It was a community effort, yeah.
And Jestadeva wasn't alone in this endeavor, right? There were other absolute titans of astronomy operating in this school over the next 2.5 centuries.
Oh, absolutely. It was a thriving lineage. You have figures like Paramasvara, who was a direct disciple of Madhava. Paramasvara developed a new astronomical system called the Draganita.
Okay, what was his specialty?
What set him apart was his ferocious dedication to empirical observation over pure theory.
The sources have a wild statistic about him.
They do. The historical record notes that Paramasvara personally meticulously observed the night sky and documented every eclipse and planetary alignment for 55 continuous years.
Wow.
He spent over half a century looking up, recording data, purely to test and refine Madhava's mathematical models against the physical reality of the sky.
I mean, talk about dedication to the scientific method. That is 55 straight years of QA testing the code to make sure it doesn't break in production.
Precisely. And the lineage continues with Nilakantha Somayaji, who authored a seminal text called the Tantra Sangraha. Nilakantha was a staggering transcendent genius.
What did he discover?
By analyzing the data from Paramasvara and others, he managed to correctly formulate the equation of the center for the interior planets, Mercury and Venus.
And just to put that in historical perspective, he did this roughly 100 years before Johannes Kepler figured out the exact same planetary mechanics in Europe.
A full century before Kepler. And we also must mention Acciuto Pizarrotti. He made a massive breakthrough in spherical astronomy by discovering the formula for what's known as the reduction to the ecliptic.
Okay, and when did the West figure that one out?
In the Western historical tradition, this complex spherical calculation was first published by the famous Danish astronomer Tycho Brahe, but the texts prove that Acciuto Pizarrotti had already formulated and utilized it in Kerala long before Brahe.
It really just makes you rethink everything you thought you knew about the history of science.
It's a complete paradigm shift.
If we pull back and look at this whole lineage, from 1340 to the 1800s, I keep coming back to this specific analogy. The Kerala School functioned exactly like a highly funded, multi-generational university laboratory.
Very accurate comparison.
You have Madhava acting as the brilliant, radical principal investigator. He is the one who lays down the groundbreaking theoretical framework. He invents the infinite series, he conceptualizes the infinitesimally small, he creates the first forms of calculus.
Yep, the visionary.
And then for the next 250 years, his academic descendants, his graduate students, his postdocs, generation after generation, take his raw theory and rigorously test it against the physical universe.
They do the legwork.
They observe the sky for decades, they refine the error correction algorithms, they publish massive step-by-step textbooks in the vernacular language, and they perfectly track the movements of the cosmos.
It was a sustained, highly systematic, and incredibly disciplined enterprise of scientific discovery. They possessed a consistent logical formalism, using methods we unmistakably identify today as calculus, and they applied those methods with devastating success to understand the physical universe.
Okay, Sigma scholars, let's take a breath and recap the incredible timeline-shattering journey you are about to embark on.
It's a lot to take in.
We started by exploring the humanitarian, integrated, and fiercely observant culture of the Nila Valley, a society where poets were mathematicians and the pursuit of knowledge crossed social boundaries. We saw how the vital societal need to accurately predict the physical world, to know when the rains would come and when the sun would hide, drove the staggering mathematical breakthroughs of Madhava.
Necessity truly is the mother of invention.
And now you have the historical blueprints to translate that 14th century genius into 5 distinct modern Python programming projects.
You are going to generate Katyayati encrypted trigonometric arrays. You are going to build a dynamic time series moon tracking algorithm based on anomalistic cycles. You're going to run infinite pi loops and then drastically optimize those loops using algorithmic convergence acceleration.
So cool.
And finally, you're going to model the Sankalita method of geometric integration using dynamic asymptotic limits.
It is a tremendous workload. But by writing this code, you aren't just doing a homework assignment. You are actively participating in a mathematical tradition that spans centuries and continents. You are connecting your keyboard to a stylus on a palm leaf.
And as you open up your code editors and begin to type, this journey raises one final, deeply provocative thought for you to consider. Throughout this entire deep dive, we've seen that the Kerala School's unique native approach to calculus, specifically their method of performing complex algebraic summations before taking the infinite limit, was highly successful, perfectly logical, and computationally brilliant.
Right.
But it is fundamentally, structurally different from the European method of taking the limit first, which is the method we use as the universal global standard today.
Because history is written by the victors, and the timeline isn't a straight line.
It isn't. So we have to ask ourselves a profound what if. If this brilliant, vernacular, highly optimized mathematical tradition of the Kerala School hadn't slowly gone into decline by the 1800s due to a complex mix of historical shifts and colonial pressures, what entirely different branches, frameworks, or methods of advanced mathematics might we be using today?
That's a huge question.
If Madhava's method had spread across the globe and become the definitive version 3.0 of human mathematics, how differently might we understand the physics of the universe right now? What undiscovered physical laws might a different kind of calculus have revealed?
Wow. If the source code of modern physics was written in Malayalam instead of Latin, imagine what that universe looks like.
Sigma scholars, you have your parameters, you have your history. Get to work.